as of today, the bell ringers and the cool downs will be graded for accuracy. They're worth 5 points. If you get it correct, you get all 5 points. If you don't get it correct, you only get 3 points. So I want you to try your best. Okay, go to the first page that is in your handouts. We're going to look at special segments and triangles. The first one is the median. It is a line that connects a vertex of a triangle to the midpoint of the opposite side. So you can fill in those blanks, vertex and midpoint. And what it does is, here's my vertex, and here's the midpoint of that side. And I know it because if I make these two marks, those little parts are the same. So that is called the median. The next one is called the perpendicular bisector. It does the same thing. It's a line segment that cuts a side of a triangle in half and makes a right angle. So cuts it in half and makes a right angle. The next part is angle bisector. It's a line segment that cuts an angle of a triangle in half. So here's my angle. It comes from my vertex and it cuts it in half. So two little arcs, like one arc in each angle, means they're the same size. Then we have the altitude. It is also known as the height, and is a line segment that starts at a vertex of a triangle and is perpendicular to the opposite side. It is perpendicular to the opposite side. So here's my vertex, and here's my opposite side over here, and it is perpendicular. It doesn't cut it in half. It just comes from the vertex and is perpendicular to the opposite side. All right, the next part, it says sketch a perpendicular bisector through side EF. So it needs to go to that. So perpendicular bisector, if you look up here, it doesn't come from a vertex. It just comes from another side. So it needs to either come from this side or this side, and it needs to cut this side in half and makes a right angle. So if I make it come from this side, it'll probably look something like that. All right, which special segment creates a right angle but does not necessarily bisect a side? So which one of these four up here has right angle and doesn't bisect a side? It may, but it doesn't always. So there's only two that have right angles. Which one doesn't bisect the other side? What type of special segment is shown? So which one bisects that opposite side, but it comes from your vertex? Which special segment is shown? So it has a right angle and it bisects the other side. Notice it does not come from a vertex. So look at the ones above and see which ones. Number 5, sketch an altitude starting at A. So you want that altitude to come from here. Where does it go? What does it do? And then 6, sketch triangle MNO with an angle bisector MP. So here's M, N, O. Now make them by the angle bisector starting at M, and the end point of it will be P. So you're going to have to make the P. Okay, we're going to the next page. Triangle centers. When 3 special segments in a triangle meet at a point, they create a triangle center, or a point of concurrency. This is how you spell concurrency. The 4 triangle centers are in the chart below. So first space is point, second one's point, and the next one's concurrency. What concurrency means is you have 3 or more lines that cross at the same point. So those are intersecting, but if you add another one in there and they cross at the same point, now they are concurrent lines because they all cross at the same one. All right, the first one is a centroid, and it uses median. If you remember from the page before, the median comes from a vertex and cuts the opposite side in half. So here's our first median, and it cuts that in half. Here's our second one, and it cuts this side in half. And here's our third one, and it cuts this side in half. All right, and this part right here, it's called our centroid. Okay, they can be in different places depending on what kind of triangle you're using. So no matter what kind of triangle, acute, right, or obtuse, the centroid is always inside the triangle. Centroid is always inside of the triangle. Just wanted to label that for you. You may want to label it. And then the triangle's center of gravity. So in this one, you're putting triangle's center of gravity. So if I cut this triangle out of a piece of cardstock and I rested it on the eraser of my pencil where that centroid is, it would balance. It wouldn't fall off. All right, the next one is called the circumcenter. The circumcenter is used with perpendicular bisectors. Remember, they don't necessarily come from the vertex. They cut the side in half and cut it with a right angle. Okay, so this is my circumcenter. And the thing about it is, it is equidistant, if you want to write this also. Or equidistant to the vertices. Which means that point, although it's made up of perpendicular bisectors, if we measured from this point to each vertex, it would be the same distance. So if this was 4 inches, that would be 4 inches, and that would be 4 inches. They don't always have to be 4 inches. It's just the same. And I can show you that by making these marks. Because we already have 1, 2, and 3 used in that, I have to use 4. And if I took a compass and I put it on this circumcenter and open the pencil up to a vertex, I would make a circle, and my circle's terrible, but I would make a circle that would reach each one of these. Let me see if I can make it a little bit better. That circle would reach each vertex. Mine's terrible because I don't have a real compass, but all right, starting on the right box of that, if it's an acute triangle, it's inside of the triangle. So this triangle that we were given for our diagram is an acute triangle because it is inside the triangle. Acute, remember, acute triangle means all of the angles are acute, smaller than 90 degrees. If it's a right triangle, it's on the triangle. So if I have a right triangle, then it is going to be somewhere on that triangle. All my lines would cross in that one spot. So if I look at this, it would go here, and then this one would be here, and then this one would be there. And so it would cross about right there. And then for my obtuse triangle, it is outside of my triangle. So if I have an obtuse triangle, remember that is one angle is bigger than 90 degrees. I can do better than that. One triangle is bigger than 90 degrees. One angle. So if I, it would just probably be out here somewhere. All my perpendicular bisectors would be out there. All right, the next one is called the incenter. and it is made up of angle bisectors. If you look, these are cut in half. And this is my in center right there. Always inside the triangle, no matter what kind of triangle it is. It's always inside of triangle. And it is the center of an inscribed circle. Inscribed circle. And I notice I missed one for the one above it. So the circumcenter of a circumscribed circle, which is this circle. A circumscribed circle makes a circle in each part. Each angle touches that circle. Inscribed means that it is equidistant to the sides. So once again, if I were taking a ruler and I measured where I could make a 90-degree angle to each side, these would all be the same length, and I could put my compass point right here on that in center and make a circle that touches each side. Let's see if mine will do. That's pretty good. So it would touch each side perfectly. It wouldn't go outside like this one did. Let's see if I can just freehand it. Yeah, that's better. So that is called a inscribed because it's inside that triangle. Inscribed circle. All right, the last one we have is our orthocenter. It is made of altitudes. Our altitudes, remember, go from the vertex to a right angle. So these are all here, and this is my orthocenter. If it's an acute triangle, it's inside of the triangle. If it's a right triangle, it's on a triangle. And if it's an obtuse triangle, it's outside of the triangle. So just like my circumcenter up there, it's in the same spot for my orthocenter. So tomorrow we will take these and put them in the next worksheet. Make sure you go do your cool down now.